Today's a wonderful day because we get to combine two of our favorite things, trigonometry and integration. And it's going to be a beautiful combination. And this is actually really important. You see, trigonometric functions, what do? Well, they're functions which repeat themselves on a regular basis. So anything, phenomenon, whatever you like, which is periodic, can be modeled by the use of these trigonometric functions. So it's good that we learn how to deal with them in terms of integration. Now the basic theme is to say, look, there's a handful of things we can integrate, and how do we manipulate to get down to those? And this is our chance to show off all those wonderful skills we learned in those trigonometric identities to help us rewrite our integrals to get us something that we can do. Well, let's begin. So, what do we need to focus on? Well, we really need to focus on saying, hey, let's learn to simplify it down to something we can handle. Now, what's something we can handle? The list of functions that we know how to integrate is actually not that long. In terms of trigonometric, we can integrate sine, cosine, secant squared, secant tangent, and secant by itself, and tangent by itself. So those are the functions that we know how to integrate. So when we talk about trigonometric integrals, it's not that we're going to add a lot of new different functions onto our list, but rather say, how can we use our identities to get it down into one of these categories? There is actually one other thing that we know how to integrate, of course, and that is we know how to integrate polynomials. Now you're probably thinking, polynomials? That doesn't belong on our list. Those aren't trigonometric. But see, one of the things we can learn to do is by appropriate substitution, we can transform a problem which is trigonometric into one which is algebraic. It's that ability to hop back and forth, which is very good. So in addition to practicing our trig identities, we're also going to be thinking about, hey, let's look for good substitutions to make so that we can transform things into polynomials. And we love polynomials. They're great. Now, in terms of identities, there are tons of trig identities. There are books full of them. And so you might be starting to be like, oh, do I really have to memorize books full of formulas? And the answer is no. You have to memorize 6. As far as I'm concerned, there are 6 key identities which will get you through. What are they? Well, conveniently enough, we wrote them down. So they fall into 3 groups. There's what we call the Pythagorean identities. Sine squared plus cosine squared equals 1, and tangent squared plus 1 equals secant squared. Now the reason we call them the Pythagorean identities is they really are just another way of expressing the Pythagorean theorem. Okay, the next set are double angle. And it gets its name because it deals with double an angle. So namely, sine of 2 theta is 2 sine theta cosine theta. Cosine 2 theta is cosine squared minus sine squared. The last piece, the last pair that you need to know are called power reduction. And the name kind of gives it away. What is it we're trying to do? We're trying to reduce the power. So in particular, we have the following. Cosine squared is 1 plus cosine 2 theta divided by 2. Sine squared, 1 minus cosine 2 theta divided by 2. And if you look, where are they coming from? The power reduction identities come from a combination of the double angle identity and the Pythagorean identity. So these are the 6. As long as you know these 6, then you'll be able to handle everything that we talk about. There are some other trig identities, and we'll point a few out, but they're not the ones that you need to have completely memorized by heart, and not the ones that we're going to be focusing on for right now. All right, so let's talk about a couple of different situations. How do we handle them? What do we do? So let's start with our sort of bread and butter. When it comes to trigonometry, oftentimes we say, hey, think about sine and cosine. And there's a nice rule of thumb which says, when in doubt, reduce to sine and cosine. Now, why? Well, because every trig function there's a nice way to rewrite things in terms of sine and cosine. So if we know how to integrate sine times cosine, we're in really great shape. And so this will get us a lot of the way there. So what do we have? Well, we have some power of sine and some power of cosine. So what do we need to do? Well, we need to think about what's true. Well, one of two things is true. Either one of our exponents is odd, and then we're like, woo, yeah. Or they're both even, and we're like, ugh. Okay, so how do we handle that? Well, the one of the exponents is odd is a fantastic idea. It's a really, really simple. So what it comes down to is substitution. And here's another nice rule of thumb to remember. You see, if I have a sine squared of something, so I'll call theta, doesn't really matter, it's more or less the same as having a cosine squared of something. So in other words, if I have a sine squared of something, I can replace it by something that looks like a cosine squared. If I have a cosine squared, I can make it look something like a sine squared. That's the Pythagorean identity that says sine squared plus cosine squared equals 1. So what happens? If you have an odd power, let's say you have cosine to an odd power. What we can do is we can pull a single cosine out, then we have cosine to an even power. And we say, well, wait a second, cosine to an even power is essentially sine to an even power by using the Pythagorean identities. So I have really some powers of sine, and then really the truth is there'll be like a big long expression, things breaking down together, but that's okay. The important thing is it's a bunch of stuff with sine, and then there's a single cosine on the back. Perfect. You substitute u equals sine of x, and what happens is that this little piece on the back is your du. So it becomes an integral that's an algebraic polynomial, and life is good. Now, what if you have sine to an odd power? Similar principle. Pull out a single sine, put it on the back. Okay, now that it's on the back, say, look, my sine to an even power, I can make it look like a cosine to an even power. So what I really have is cosine to some power times a sine. You say, perfect. Let u equal your cosine, and then du becomes sine. Technically, there's a negative involved, but we're able to handle a negative sign. Okay, great. So that's how we deal with one of the powers is odd. Well, what if they're both even? Well, if they're both even, then we say, perfect. Pull out your power reduction identities. Now, when we talked about power reduction, we said there were two of them. Secretly, since we're between friends here, and I'm going to let you in on a little secret, there's three. You're like, what? There's three? What are they? Okay, so there's the two which we explicitly talked about, which is cosine squared is 1 plus cosine 2 theta over 2, and sine squared, which is 1 minus cosine 2 theta over 2. The last one is from the double angle identity. So if you divide both sides by 2, you can say, look, sine times cosine becomes what? Well, it becomes sine of 2 theta divided by 2. All right, perfect, perfect. Now, you might say, which ones do you use? And here's my preference. I like to use this as much as possible. Now, you might say, but wait, Steve, they're all about power reduction. Why give this one special treatment? Well, I'll tell you why, and it's very simple. There's no plus or minus. You see, I think a lot of times that we make mistakes is when we start adding in little terms where you have to be like, oh, I got to expand, and I have this expression with 1 plus something times 1 minus something squared, and it gets us into trouble. So when we use this fact that sine times cosine is a half sine of 2 theta, we don't have to use any addition or subtraction. That means life is beautiful. It simplifies really, really well. All right, so there we go. That's sine times cosine. Now, there's another related set, which is secant and tangent. So sine and cosine go together well, and so do secant and tangent. Now, the reason they go together so well is if you think about things like the derivative of secant is secant tangent, derivative of tangent is secant squared, so that they're connected by their derivative. So it makes sense to put them together. Now, how do we handle it? There's a little bit more subtle. See, with sines and cosine, it's very easy because the derivative of sine is cosine, the derivative of cosine is negative sine, and life is good, life is great. But with secant and tangent, it's a little bit messier. So really, there's a couple of cases. So what are they? Well, the thing is, we have this lovely identity, the Pythagorean identity, and we say, that's going to be the key. And with that, we can do one of three things. One thing we can do is say, if I can make it look like a tangent of stuff, so an expression just involving tangent times a single secant squared. Perfect. See, because if we substitute u equals tangent of x, then this last term here, secant squared x dx, is our du, and we're off to the races, off to algebra. We've gone. Life is good. Now, that's not the only possibility, of course, because not everything can be done that way. But it might be the case that we can say, oh, by rearranging, we can write it, so it looks like some power of secant times secant tangent. Perfect! Look, substitution. U equals secant, then your secant tangent becomes a du. So one of the things you start by doing when you see an integral like this is if you say, okay, can I pull off the secant squared to the side, and is everything that's left, can I put it in terms of tangent? Or can I pull off a secant tangent to the side, is everything that's left in terms of secant? Now, there is one last case, and this is the case that's going to make us go, ugh! You can't do it everything. The last thing that could happen is if you have secant to an odd power. Well, the short answer is, if you have secant to an odd power, a difficult journey lies ahead. And we're going to go through this as we do some of our practice. And it's not so easy. And what happens, I'll go ahead and tell you the story, is when you have secant to an odd power, you do what's called the reduction identity. Well, so maybe you have like secant to the 11th. Well, through a little bit of manipulation, you can say, okay, the integral of secant to the 11th is really like the integral of secant to the 9th with some extra stuff. Like, okay, well, now I have secant to the 9th. That's progress. Smaller. All right, well, secant to the 9th, you can say, okay, reduction becomes secant to the 7th. Aha! And that comes secant to, and then eventually you get down to secant with all this extra stuff along the way, and we at least know the integral of secant. It's that fun integral. The integral of secant is log secant plus tangent. And therefore, if we're able to reduce down to secant, we can succeed. The other thing to keep in mind, of course, is we do know the integral of tangent. The integral of tangent is log of secant. I actually like integrals involving secants and tangents because they're a little bit more interesting. There's a little bit more flavor of things you can do. All right. Well, as we go along in our menagerie of things we can integrate, we run into things look like this. So square root of 1 plus or minus cosine theta, or square root 1 plus or minus sine theta. So these are kind of highly specialized, very, very specific. And but we should talk about them. It's examples of using our trig identities. So how do we do it? Well, there's a couple of choices that you have. And let's just talk about things that you can do. You'll see there's sort of 2 bullet points, which means you really have 2 possibilities. So one thing you can do is you can say, hey, I really want to get rid of, let's say I have square root of 1 plus cosine theta. What's our goal with square roots? Our goal is to get rid of them. It's not like we're really anti-square roots. It's just they're hard to deal with. So it's like, okay, let's let's get rid of them. So we think about it and say, we'd really like the inside to be a perfect square. That's a great way to get rid of a square root. Now you're probably thinking, Steve, it's just easier. Pull out the eraser and erase it. But no. That changes the problem. We don't want to change the problem. We just want to make the problem easier to work with. So what you can do, this is a beautiful idea, which says, hey, 1 plus cosine, it's not terribly off from 1 minus cosine squared. And the reason why we like that is 1 minus cosine squared is sine squared. So you can imagine I multiply on the inside, because I've got to stay inside the square root so that I can make this work. So our square root has gotten bigger now. And what you'll end up with is you end up with the square root 1 minus cosine squared over 1 minus cosine. And at this point, you're like, well, this is true. Maybe it doesn't feel like we made progress, but then we're like, aha, but 1 minus cosine squared is sine squared over 1 minus cosine. And now we're like, whoa, yeah, progress. And at this point, we're like, well, the last thing to note, what's the square root of sine squared? And I know what you want to say. You want to say, it's sine, Steve. We saw the sign, and it opened up our eyes. We saw the sign. Except, it's not. Can you see why? You have to be careful. There's a little note. It's actually the absolute value. And then this is a time when you say, okay, well, let's think about what you would do with the absolute value and be careful. But at any point, really, our new integral says, hey, you have a sign by itself. Check to see what to do with the absolute value. Usually we can get rid of it, and then life is good. We're ready to go. Perfect. Now, that's one approach. And essentially what you're doing is you're using conjugation to pull out something out of the square root that can act as a du part, right? To make because now what would you do? You'd say, hey, let u be the 1 minus cosine, then du looks a lot like sine. So that's how we would finish it from there. The other thing we can do is power reduction. So there's a couple of possibilities. So it turns out, for instance, 1 plus cosine is 2 cosine squared of a half theta. This is just taking the power reduction and rewriting it in a different way. Similarly for 1 minus cosine. And 1 plus or minus sine turns out it's a little bit of work, and you can check this later. If you don't believe me, just expand it, and you'll see it becomes like sine of half theta plus or minus cosine of a half theta squared. So what does that mean? Well, for instance here, we could have said, look, the square root of 1 plus cosine theta is really the same as the square root of 2 cosine squared of a half theta. Great. Which is what? Well, that's the square root of 2 times absolute value of cosine 1/2 theta. And there we go. And off we go, and we're in business. And it's not so obvious that these two are the same. Not obvious at all. But that's all right. It's still true. Even if something isn't obvious doesn't mean that it's not true. So there you go. Okay, well, one more little topic. Now, the following topic uses some identities which I don't have memorized by heart, and I really don't expect you to. Keep in mind, I may not be your calculus teacher, so you should always figure out what your calculus teacher wants. But while we're here, we should at least mention them. So what if you have something that looks like the integral sine ax sine bx? Or it could be sine ax cosine bx, or cosine ax cosine bx. And these are important integrals. They do actually serve an important role. There's a topic called Fourier series, which we're not going to get into. But for that, you do need to know how to do these integrals. The way we do it is that, believe it or not, there's an identity. And for instance, you say, hey, there's this nice fact that sine of ax, sine of bx, it's really a difference of 2 cosines. cosine of a minus b times x, cosine of a plus b times x. And once you know your sum and difference formulas for cosines, it's actually fairly easy to verify that these are true. And the point here is if you have sines multiplying together, but the insides are sort of incompatible. So we really want the insides to match up. So if they don't match up, we're like, ah! So in that case, what we do is we say, okay, what we can do is we can use one of these facts and rewrite, and life is good. And of course, there's a million other trig identities. You'll never run out of trig identities. It's just a wonderful, wonderful thing. But a lot of it is just being comfortable with basics. Don't go into this thinking, I'm going to go and know every trig identity. Because that's not as helpful as saying, let me start with these really important 6 identities that we talked about at the very beginning. Know them well. And then know how to use them and play with them. Because it's not about how much you know. It's really about how well you're able to use what you know. And being able to get better at using what you know comes down to practice. Okay, so I think it's time for us to transition over and do some practice. Hope to see you soon.